All right, good morning. So obviously we're not in person today. Bit of a snowstorm issue. Okay, if you haven't done so already, pin my video so that if other people end up making a sound, it doesn't completely jump away from my screen. So today I'm going to be doing a review of chapter 8. On Friday, we'll do the syllabus stuff when we can be in person and I can print it out. So, chapter 8. This is not the pen I want. Yeah, sorry, I'm going to try to keep this in a pretty good position. So I'm going to start off by reviewing some nomenclature. So we have something like this here. This is a 4-carbon chain. This would be considered a butane with an A and E here. If we have a double bond, so this whole chapter is about double bonds, so that's what we're going to be talking about. Something like this. This is going to be a butene. There's two different types of this butene we can have. We can either have this one, where our substituents are on either side of this double bond here. So this would be considered a trans butene here, versus if we have the other one where our two substituents are on the same side of our double bond. This is going to be a cis butene here. Getting into a slightly more complicated version of this, we can have E and Z, which E is essentially trans and Z is essentially cis here. I'm going to throw up a molecule. So, can I record this? Yeah. If we have something like this here, what I usually tell people to do is just kind of cut your double bond in half. Down this center line here, and then we can use our normal R and S naming conventions. So to prioritize the groups. So we have an ethyl versus an H here. So this would be a higher priority group than this H on this left side of our molecule. Taking a look at the right side, we have an ethyl versus a methyl, which makes our two highest priority groups on the same side, just like they would be on a cis bond here. So this is going to be a Z alkene. Similarly, if I take something like this here, cut it in half again. Our left side is similar to what's over there, so our highest priority is going to be this ethyl group as compared to this methyl group. On the bottom here, we have a fluorine versus a CH3. Our fluorine is going to be our higher priority. Our highest priorities are on opposite sides, kind of like a trans double bond here. So this is going to be an E alkene. Plugging this into an actual molecule and doing a naming for it. So let's start with something that looks like this here. So we have a chiral center on our bromine. First thing you want to do is figure out what your longest chain is going to be. If you have an alkene, it has to go through the alkene, which helps a little bit. So there's no way it could be like 1, 2, 3, 4 here. So our options would either be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. So 6 is longer. So it's going to be a hexene. We have two different possibilities for naming or for numbering. So you can always either go left to right or right to left on these. For an alkene, you're going to pick the one that goes through your alkene first. In this example, it won't actually matter. So let's number from left to right. So we could have 1, 2, 3, 4, 5, 6. Or we could have 1, 2, 3, 4, 5, 6. So taking a look at this molecule here, if we go 1, 2, 3, we hit our double bond. Or if we go right to left, 1, 2, 3, hit the double bond. So in this case, it doesn't matter. We have to go to the next highest priority, which is going to be this bromine. So 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6, meaning that it will give us a lower number if we go from right to left. I'm going to kind of cross out all these red ones. We can name some of these. So on 2, we have a bromine, so it's a 2-bromo. On 4 here, we have a methyl group. So for methyl, I'm going to redraw this to do a little bit of stereochemistry. So let's do the E and Z first. Breaking this in half here. Our 2 priority groups, we have ethyl versus methyl. So ethyl is going to be our higher priority. And then we have H versus this bromine with carbon over here. So this is going to be our higher priority. These two are going to be E to each other. And then taking a look at R and S for this bromine, we've got Br is going to be our highest. I'm going to redraw it. It's going to get messy. Br is going to be our highest priority. We have carbon with all the stuff off of it, just a CH3 over here. So this would be 2, 3. Br is in the forward position, so we don't need to flip anything. This is going clockwise. So this is going to be R here. Putting it all together, we're going to start with first naming our stereochemistry. So the R is on 2, the E is on 3, so we'll put them in numerical order. This is going to be a 2R, 3E, putting these in alphabetical order, 2-bromo, 4-methyl. Our double bond is on 3, so 3 hexene. Oh man, it's having trouble focusing. I'll also post all these lecture notes online so you guys can go through and double check them for things like this, where it's really hard to see spelling. It'll be better when we're back in the lead center on Friday. It's a little easier to see on that screen projector. I'm going to do one more slightly more complicated example and then go into some reactions. So let's see. Nope, did it wrong already. Okay. 2 CLs. Okay, we are going to take this example here. there's really only one carbon chain, so it doesn't really matter how you do it. So it'd be 1, 2, 3, 4, 5, 6, 7. So this is a heptene. So it has a double bond. Hept for 7, ENE for double bond here. Naming some of our we should number it first. So you want to number it, so you go see your double bond first. If we go from right to left, it would hit the double bond at 1, 2, 3, 4 versus 1, 2, 3 going left to right. So left to right gives us a smaller number. 1, 2, 3, 4, 5, 6, 7 here. That help? That did nothing. Okay. So looking at our molecule, on 2, we have an iodo. On 5, we have a bromo. On 6, we have 2 different chloros. And then breaking these into, let's do E and Z first. So this is clearly trans, which means it's going to be an E alkene here. Looking at R and S for this first one, we've got I is going to be our highest priority, followed by this large methyl chain, and then lastly this CH3 here. So this is going counterclockwise. This is going to be S. I'm going to redraw it. To do this bottom one, so for this BR here, we have bromine's going to be our highest priority group. We have 2 chlorines and a carbon here. Double bond, we treat it like it's 2 separate carbons. So this would be the equivalent of this here, where it's essentially, you're treating it, this double bond, like it's 2 separate bonds to carbon. So this is bonded to chlorine, which is going to make this a higher priority group here over these 2 CH3s. So this is going to be our number 2. This is going to be our 3. This is going clockwise. So it's going to be R. So naming it, starting with our stereochemistry. So we have A2S, our double bonds on 3, so 3E. Our BR is on 5, 5R. Putting these in alphabetical order. B is going to come first, so 5 bromo, followed by our chlorines. So there's 2 of them, so it's going to be 6, 6, di, chloro. You kind of ignore the di when you're doing the number or the alphabetical order. You have an iodo on 2, so 2, iodo, and then 3 heptene. Okay, so that's nomenclature. Hopefully that's a bit of a review for you guys. We're going to look at some of these reactions. The first reaction is pretty simple. So if I take well, let's first talk about making double bonds, and then we can go into reactions for them. So to make a double bond, really you're just doing an E2. So if you throw in some sort of a base, And I'm going to use H minus as a really simple base. We can pull off a proton, eliminate a Cl, and form our double bond here. We have something slightly more complicated. Whoops. Like this molecule here, we now have a couple of different protons that are possible. So we have secondary protons that are alpha to our Cl, as well as these primary ones. If I throw in a small base, such as NaH here, this is going to be selective for one of these two secondary groups. So we can pull off one of these protons, eliminating Cl. And that will give us this alkene product. To generate the other alkene product, taking the same starting material and instead throwing in a large base, such as LDA, lithium diisopropylamine here. This is going to be too large to pull off one of your tertiary or your secondary protons here. It's going to take one of these easier to reach primary ones. And give you just this product where you form your double bond between your primary and your tertiary position here. So that should be a little bit of a review from E2 reactions. Once you have this double bond, there's a whole variety of things you can do. The simplest one is if we throw in something like HCl here, our double bond can pick up a proton. We're going to generate a carbocation. From here, our Cl minus can come in. Do a nucleophilic attack. And we'll do a single addition of chlorine here. We can do this with a couple of different reagents. So I'm going to kind of make it a little bit simpler. Throw in HCl, single chlorination at our more substituted position, throw in HBr. Same concept. We can do the same thing with water and acid. Can either be drawn like this or as H3O plus. All of which give you this same product here. Red for a little bit. Okay, so if we have something a little bit more complicated, let's see, does red show up? Red shows up, okay. If I throw in H plus with this, compound here, at this point, when we do our nucleophilic attack. We can generate a carbocation. This is a secondary carbocation. It's next to a more stable center. It's next to this tertiary center. So this can do what's called a hydride shift. So what hydride is, if you think of just hydrogen, H plus, as a proton, and then H dot or H radical would be hydrogen. Hydride is the exact opposite of a proton. It's H minus. So it has two lone pairs. And what essentially that is, it's going to be the H plus the bond. The bond is the two electrons that go with it. So when you shift this whole system over here, we now create a tertiary carbocation, which can be attacked by our water. We're going to lose a proton. Put this H over there. And form this hydride shifted product. So when do you do a hydride shift? You're going to do a hydride shift when you have a secondary next to a tertiary. If you have something like this here, when we get to our dying, carbocation, this is secondary. The center next to it is secondary. If you were to do a shift, you're not gaining any stability here. You're going from a secondary to a secondary. So this is unlikely to happen because of that. You need to be going up in stability in order to actually drive these reactions forward. So if you're ever questioning whether or not you should do a rearrangement, if you try it and it gives you something that is as stable as where you were starting from, there was no point to doing it. The other type of rearrangement is going to be a methyl shift. So a methyl shift is where you are instead of moving just a hydride, you're going to move an entire CH3. So our first step, we're going to pick up this proton here. From this point, we can shift over our entire CH3. We have a secondary center that's next to a quaternary center. My cat is crying in the background. Now when we do this shift, we end up at a tertiary center. So we again went up in stability. We went from secondary to tertiary. From here, OH can come in. Give us our rearranged product. So when you do a methyl shift, so a methyl shift is going to happen when you have a secondary that's next to a quaternary center. And that's when you'll favor a methyl shift. So avoiding these in general, if we take something like this same compound and we throw in mercury acetate, yeah, it's way too big. Sorry, trying to find markers at work. What this is going to look like. Something like this here. Our double bond can come in. Do an attack. We'll temporarily form this carbocation, but then what's going to happen is this oxygen can close and form a three-membered ring. So because we have this positive charge, we're on a really tight three-membered ring here. If you think of like a normal bond angle should be like 114 degrees. This is clearly not that. This is 60 degrees here. So what you actually end up forming is something that looks more like this. We have a really strong bond between the primary position and the oxygen and a pretty weak one between the secondary one, or whichever one is more substituted. So because of this, when your water comes in, it's going to attack at this position. I'm going to lose a proton. And then using sodium borohydride, which is a reagent we're going to talk about later in this class, and a BH4, you're able to reduce off this OAC to get just your single alcohol addition. So to compare this to what we just did, so taking the same reagent, different reactants, we throw in H plus, H2O. This is going to do a rearrangement, putting our OH on this tertiary position. We do the same thing with mercury acetate. Sodium borohydride. This allows us to do this non-rearrangement product where we get ROH in the Markovnikov position here. I'm going to kind of quickly touch on two reactions, which we're not really going to, or talk a little bit more about when we talk about radicals. So if I take HBr and peroxide, which can be drawn a couple of different ways. This will give us our anti-Markovnikov product. Similarly, BH3THF and NaOH and peroxide is going to also give us that anti-Markovnikov product here. Okay. Some other reactions. If we want to dibrominate, so we've been currently just adding one thing. If we want to start adding two things in solution, we can take Br2. So it's a pretty similar mechanism to what we've been doing. This Br can come in, do an attack. We're going to form, I'm going to draw one of the possible carbocations. This Br can cyclize. It's going to form this positively charged bromine here. There's two different possibilities. You can either form this one or this one here. You can also signify this by a plus minus. Plus minus just means invert every stereocenter. So we had this center and this center. We flip into from wedges to dashes here. You can never make this, just so you guys know, like you can make a triangle that goes up or one that goes down, but you can't make one that like goes up and down geometrically. This like can't happen. So your only two options when you're making these three-membered rings are the both wedges or both dashes. From this point, our other Br can come in and do NSN2. So I'm going to show it attacking this center here. In this case, they're kind of both the same, so it doesn't really matter. We're doing an SN2, so we're going to be inverting our stereochemistry. This was a wedge. It'll now be a dash. Giving us this anti-product. And you can attack the other stereocenter and get you the other products. That's why you have this plus minus here. We can also do this reaction in water. Which will change our nucleophile in this step over here. So throwing in Br2 is going to get us to this point. Our Br can cyclize like it did before. we are going to make this intermediate. So this looks a lot like this intermediate that we were forming before. And in the same way where you had a secondary, tertiary position, secondary, tertiary position, our bond between this oxygen and the more stable position is going to be kind of stretched. It's going to look something like this. So because of that, when our water now comes in, because we're in water for this case, it's going to want to attack at this more substituted center, kicking out BR. This center is untouched. So you'll flip the stereochemistry of that center. With the proton. Giving us this anti-addition of Br and OH here. The last type of these, so this is also a plus minus. We also could have made the dash version here and then came in and gone the opposite version of this product. The last type of reactions I'm going to talk about is adding two oxygens. So this is going to react in a very similar way to what we just did. So if I have a peroxy acid, something a couple of different ways you might see this. MCPBA is an example of one. It's very commonly used. Essentially what it is it looks like a carboxylic acid, but has another oxygen. So there's a peroxide there. These are peroxy acids. And what they will do is give you a peroxide. Or sorry, an epoxide. And when you throw in H plus and water, the first step is going to give you this protonated epoxide here, which should look really similar to what we just did with Br, which should look really similar to what we did a little bit ago with OAC. And these all kind of work the same way. There's going to be a little bit of a positive charge on this tertiary center versus this secondary center. So when this water comes in, does a nucleophilic attack, it's going to do an SN2 at this center. Going to be a little bit of a proton shift. We are going to keep the stereochemistry we had down here. And then flip the stereochemistry we had up here. To give us anti-OHs here. And this is also a plus minus. You could also have a wedge here and a dash here. The other reaction is, I'm not going to go over the mechanism for this, but if you want to add a syn, you can add osmium tetraoxide. NaHSO3 and water. This is a large planar molecule. It's going to come in, add the H's, OH's to the same side, giving you the syn addition. And in a similar fashion, I'm not going to talk much about this one, but this is a pretty straightforward reaction. If you add an H2, it's also going to give you a syn addition of H's. For the most part, it's just going to reduce your double bond to a single bond. Okay, so that is a pretty quick review of chapter 8. I believe we're starting chapter 9 on Friday, which should be some new reactions. A lot of them are very similar, so we'll probably go through it pretty quickly. That class should be in person at the Lead Center. If you guys have any questions, feel free to either stay on this Zoom meeting or send me a message. We can set up a time. I think office hours are going to end up being from noon to 2 every day. And they'll be on the same Zoom chat as the class. So if you guys have any questions, feel free to chime in. If not, I will see you guys later. Someone asked me if I can upload the notes. Yes, I will upload the notes. So yeah, exams are going to be in person unless you're unable to, which case send me an email and we'll figure out a different situation. So those are days when we would want you guys to be in class. Using the cam during lecture on Friday. Yes, I'll be using the doc cam for the lecture on Friday, which tends to work a little bit better than this. And I will send out I can send out recommended book problems, but I'm also going to post practice problems just in general with answers to these probably at some point during today. There's always a Zoom component for the class if you guys want to come over Zoom as opposed to in person. And I'll also post links to the Zoom videos whenever I get them uploaded. It'll probably just be from one class, so it'll probably be from the 9:30 class, so it might seem a little different, but it's the same material. Do we have a recitation meeting? Yeah, so there still should be recitation on Thursday. If you had it on Tuesday, they will record it if you want to watch it. There won't be a quiz this week, so it's kind of up to you whether or not you want to see what they're doing in recitation or not, but it will be available. With the practice problems you post, there will also be recommended book chapters. Yeah, I'll post what chapters I recommend. I mean, I'll tell you in the lectures what material we're not covering, but for the most part, it's going to be the full chapter unless I say otherwise. Okay. Anybody else? If not, I'm gonna cut it so it starts processing the recording.